Hey everyone, this is Dr. Walker. In this video, I'm going to go over an example from v572, the Biot-Savart law. In this example, we want to calculate the magnetic field due to a curved wire segment. The segment is shown. It consists of a straight segment here, and then a curved segment here, and then another straight segment over here. The variables that we are given in this problem is the current I, and then the radius of this circular arc here, which is A, and then the angle theta subtended by the arc. So let's take a look. Let's break up this wire into three segments. So let's look at segment 1 here, and then we can look at segment 2, and then we will look at segment 3. Let's write down the Biot-Savart law. dB is equal to mu naught over 4 pi I ds cross r hat over r squared. So the first step in using the Biot-Savart law is to go ahead and label our length element ds that has a direction in the direction of the current. So let's draw a little ds right here for segment 1. And then the next thing is to draw the r hat vector. The r hat vector points from ds, and then it points in the direction towards the point at which we are trying to calculate the magnetic field, which is point O in this case. So r hat points in the same exact direction as ds. So when we want to find a cross product ds cross r for segment 1, we know that the cross product is going to be equal to 0. And so that means that we're not going to have any magnetic field due to this straight wire at point O. We can do the same thing for segment 2. In this case, we're going to draw a ds segment pointing in the direction of the current. So ds is going to go to the right here along the segment. And then the r hat vector points from ds towards the point O. So in this case, we can see that ds and r hat are in opposite directions. And the cross product is still going to be 0 because the angle is 180. Sine of 180 is still 0. So the cross product is still 0. So the field due to this third segment, the second segment here, is also 0. So we only need to find the field due to the curved segment. Let's see how we're going to use the Biot-Savart law. Same steps. First, draw your ds, and it has already been drawn for us in this diagram. ds is going down here in the direction of the current. And then r hat has been drawn as well. It goes from ds towards the point O at which we're trying to calculate the field. It's helpful to draw several ds's to make sure that the field points in the same direction for every single segment, because that's the only way that we're going to be able to integrate is if all of the fields point in the same direction. So if we draw a ds over here, let me draw it back in blue again. If we draw a ds over here, and then our r hat is going to point towards point O here, r hat. What we notice is that no matter where we draw the ds, it will be perpendicular to r hat, right? Because the radius of a vector pointing the radial direction or towards the center is always perpendicular to a vector that is tangent to that circle. So when we used a cross product and figure out which way B is going to go, what you do is you're going to point your fingers down with your palm pointing to the left, and then you fold your fingers in the direction of r hat, And you should see that your thumb is pointing into the page. Whether you do it for this segment or this segment, no matter which segment along this curved arc here, the thumb is going to point into the page. So the magnetic field is all in the same direction. So that's what we need here. Otherwise, we would have to make some adjustments. So the cross product is going to be, let's go ahead and write mu naught 4 pi I, and then since they're perpendicular, we said in the video that the cross product ends up being just ds, because we have ds times 1 times sine of 90, which is just ds. And then the distance r squared is a distance from ds to the point, and that distance has been defined in our picture as a. So it's going to be a squared. And now we are ready to integrate. We know that the total field, and let's just focus on the magnitude of the field right now. We already know the direction was into the page. So let's find the magnitude of the field here. It's going to be mu naught 4 pi I for a squared, and integral of ds. Now we can write ds as r d theta. If you remember, we've made that substitution a lot. We can consider a tiny little arc length, ds. So we can write ds equals r d theta, where r is a. So let's go ahead and substitute that here. And you don't have to, you can just integrate ds over the entire length. It's just we don't have a length, but you could call the length s if you wanted to. So you could just integrate this and get s if you wanted to. Or we can just rewrite it. Let's just rewrite mu naught 4 pi a squared. We can just rewrite it as a d theta. And then we're going to integrate. We can integrate from an angle. We can use this as our reference point from which we're defining the angle. So our angle would be defined from 0 all the way to theta. And what we're going to get here is the angle. I was hesitating here because I wrote pi instead of theta. I was like, that's not right. There's not supposed to be a pi there, just a theta. And so when we integrate, we're just going to get the theta. The a comes out of the integral. So we're going to get mu naught I a 4 pi a squared, and then the integral d theta just becomes theta. And so this a will cancel out, and our final answer is going to be mu naught I theta over 4 pi a. If we do want a direction for the field, then we can just say into the page. And if you had just integrated this ds to get to s, then you would have had to make the substitution. At this point, for s, you would say s is equal to a times theta, and then you would still get the same exact answer. So whichever way that you prefer. So this was an example using the Biot-Savart law. We will have several more examples throughout the next few lectures, as we will find the magnetic field due to a straight wire and also due to a current loop.